Thank you so much for having me. I'm going to talk about the EMIT mission a little bit and maybe justify what it is and tell you a little bit about it. It's actually really good timing because our Nature Geoscience describing these results was actually published yesterday. So I can show you all the results here and have it be recorded. It really was a teamwork, and I'll try to tell you a little bit more about how this all happened here. But this shows you the space station and the EMIT instrument, which I can't remember where it is, but I have a slide where it shows where it was. And EMIT is not a very good acronym, but it's Earth Surface Mineral Dust Source Investigation, or it is a really good acronym as long as you don't pay that much attention to what the words mean. But a lot of what I'm going to show was done by my postdoc, Longley Lee. Rob Green is the overall PI of the project and really made sure that it was a success. And Dana Chatwick provided me with some of these awesome NASA images. Here is the EMIT team, and you can see it's a huge team. And we wouldn't have been able to do it without this whole team. And I'm sorry, the resolution isn't great here on this one, but it really is a nice group of people. So what I'm going to do is talk a little bit about dust. You folks know about it, but I might talk about some different parts of what's important than what you work on. So maybe a little bit of a introduction there, and then talk about the composition of dust and why not all dust is the same, and talk about the EMIT project itself here. So this slide I probably don't have to show you except for their very cool images. What do we mean by dust? We mean mineral aerosols suspended in the atmosphere. And of course, this can be in different kinds of storms. I like to remind people just how huge these little dust storms can be. I mean, this storm is bigger than Spain, okay? It's really these dust storms, when they come off of North Africa here into the North Atlantic, can be huge. Just to remind us all that aerosols are really heterogeneous in space and size and composition and everything. And again, I just like to show these images from the literature, just showing, so G here, this is dust, but these are the other things that are in the atmosphere all over. Here's some more dust here. And often in the atmosphere, aerosols are some kind of conglomeration of all these things. Dust is really important for changing the surface, or the top atmosphere and the surface fluxes. And so here I'm going to show kind of this classic, it's from the AR5, so it's quite old, image of the radiative forcing of the climate between 1750 and 2011. And here on the top part, we're showing the anthropogenic forcers, and then there's the natural forcers as well. Of course, we know that CO2 is by far the most dominant, so it's almost 2 watts per meter squared. It's higher now, of course. And then we have methane and nitrous oxide and other halocarbons warming the atmosphere. But the aerosols cool the atmosphere and offset some of that warmth. And one thing is that actually the aerosols dominate the uncertainty in the problem. The aerosol uncertainty is much, much larger than the CO2 forcing or any of the other greenhouse gases. And so here, if we look at a probability density function and the effective radiative forcing, you can see that this spread in the aerosols is what comes and dominates the total anthropogenic spread. So our uncertainty is dominated by the aerosols when we try to understand what's happened in the radiative forcing. And so when we think about dust in the Earth system, we can think about some events in unvegetated dry regions with strong winds where we might get dust generated. And here we've separated into 2 kinds of dust, as we'll get into a little bit later. This is kind of a simplification, of course. But in these source regions, we get the dust generated in dry, unvegetated regions, and it depends on the soil conditions and the meteorology. Once it's in the atmosphere, in the models or in the real world, it's transported 3-dimensionally with the winds, and it's subject to wet and dry deposition. Then it interacts with the incoming solar radiation and the outgoing long wave radiation, and also with clouds and chemistry while it's in the atmosphere. And then when it gets deposited onto either land or ocean ecosystems, it can interact with the ecosystems, the biogeochemistry, and for example, the iron in the dust or other micronutrients could actually change the supply and change the nutrient conditions and either enhance productivity, or they could actually supply toxins or negative impacts. The dust deposition to snow and ice can change the albedo because it's darker than white. Everything's darker than white. So for this, we're going to use climate models. You guys probably know what climate models are, but I'm going to start from the basics here. And this is kind of a classic image of what a global atmospheric model is. And when we talk about climate models, of course, we could be talking about energy balance models, or we could be talking about full complexity models, weather models, or Earth system models. And I tend to work with the big Earth system models. So that's what I'm going to use as a tool for this. What we think about is, of course, these models include F equals ma, the resolved fluid dynamical equations, plus parameterizations of things that we don't have something like F equals ma for. So something like clouds and some of the turbulence interactions. And so here's the atmosphere. We've cut up the world into all these different grids. For what I'm showing you today, we'll be using a grid of about 1 degree by 1 degree for most of the simulations. Of course, in the ocean, we'll have a similar resolution, and on land, we can have a similar resolution, or actually sometimes we run it with a higher resolution on land. Traditionally, in the models, anyway, we model kind of an average mineral aerosol, and so it's kind of some kind of yellow color. This orange is probably a little too dark. It's some kind of yellow color is what we traditionally use, and we assume 3.5% iron often. But actually, in reality, if you've ever looked at soils, which many of you probably have since you work in this area, mineral aerosols can have really different colors. You can have, white and gray, lighter colors, or you can have things like the iron oxides, like hematite, that are much, much darker, and they can be red, or if you get in a magnetite, you can get, really, really dark iron-bearing minerals that are almost black. And so it's not homogeneous, the dust. So this traditional average is not really accurate. Some regions have much more hematite than other regions, for example. Each mineral has different properties. I'm going to emphasize a lot the iron oxides here for a couple of reasons. One is they absorb the solar incoming light, as well as they have the iron for the ocean biogeochemistry. But calcite actually tends to be bright and reflects incoming shortwave radiation more, and it also has a high pH. It's basic, and the atmosphere is mostly acidic because CO2 isn't an acid, but then we've added all this sulfate, and so it can really change the chemistry of aerosols. In addition, there's feldspar as a mineral, and people think that that's a much better ice nuclei source. So we can think about the Earth's energy budget here, and hopefully all of you are very familiar with this, but we have incoming solar radiation, 340 watts per meter squared. A lot of the energy is reflected out by clouds in the ocean, and some is reflected at the surface. Then maybe a third of the incoming solar radiation is reflected back out. And that's balanced by the outgoing long wave radiation, or infrared radiation, or planetary radiation. So the incoming solar radiation, I might say insolation, I might say shortwave, and those are all synonyms. And the outgoing long wave, infrared, planetary, or long wave, those are all synonyms. And the outgoing long wave radiation, comes from the surface, but it interacts with the atmosphere, and it interacts with the greenhouse gases, of course. But it also, and it interacts with dust particles. They're big enough to interact with the long wave radiation as well as the short wave radiation. And long wave also interacts with clouds. So in equilibrium, what goes in must go out, and we're a little bit out of equilibrium, so we have a little bit of accumulation in the atmosphere. And this is what we mean by the energy balance and where we get our radiative forcings from. And you can have some intuition about this just looking at the clouds here, that the clouds are white and bright, and that's what's reflecting things back out. Our eyes actually see the visible range, and that's where most of the incoming energy is coming from, which that's not an accident. That's why we see in those waves. And you can see that the clouds, and in some cases, well, I'm not sure I see in this image any snow, but over here on the Andes, maybe we see it. Sometimes the surface can also be important. And the dark areas are absorbing the radiation, so the oceans or the forests. Let's see. So how do aerosols can actually interact here, and aerosols interact with the clouds and can change the properties of the clouds, because the cloud condensation nuclei for warm clouds come from aerosols, basically. And so they can change the properties, even make them last longer, but also make them brighter. And that matters for both the short wave and the long wave. So these clouds are so important for albedo. We can see that with our eye. And any change that aerosols might make to the clouds could be really, really important. And that's where a lot of the uncertainties come from in the aerosol cloud interactions. So when we come back to this dust image, or how we think about dust in the Earth system model, as I mentioned, we have all this different composition that dust could be, and the mineral aerosols can be, but really the iron oxides are going to be what I'm going to emphasize here for a lot of this talk, because they behave a little bit differently than the rest of the species 4 radiation. I'm going to give a little bit of an intro to the carbon cycle as well, so that we can talk a little bit about the iron impacts on the ocean biogeochemistry. So I'm just going to give you a flavor of it. Similar to the radiation, humans are modifying it just a little bit, but that leads to the accumulation of CO2 in the atmosphere, which is causing global warming. So again, I'm using an old image just because I like it better. Here we have the anthropogenic emissions, which of course are much larger now, it's about double now from fossil fuels. And this is our emissions of CO2 in gigatons of carbon per year. And this goes into the atmosphere, and we have the stock at this time, which was almost 20 years ago, was about 750 gigatons of carbon in the atmosphere. Once it's in the atmosphere, there's really fast exchanges with the ocean and the land. So the land takes up about 120 gigatons of carbon per year, and the plants that directly themselves emit 60, and then the soils and the other, the microorganisms that eat the soil particles, soil and things like that, they release then another 60 teragrams. So there's huge fluxes here, much larger than the fluxes from humans, but they're imbalanced and in equilibrium. There's 120 coming in and about 120 going out, except that we have a little more CO2 than we should, about twice as much CO2 as we should in the atmosphere. And so the land takes up a little bit extra. And in addition, humans are deforesting and perturbing the environment. And so then there's an extra flux from the land into the atmosphere, which is larger. These anthropogenic fluxes are a little larger. Similarly, in the ocean, there's again, about 90, maybe a little bit more fluxes into the ocean and out of the ocean in different places. So the fluxes into the ocean tend to be in cold places because colder water holds more gases. Warmer water holds more solids, but colder water holds more gases. So cold air goes in the high latitudes where they call it convection there, but you'll have a really cold parcel of water and it'll go down to the bottom of the ocean or deep into the ocean, and that ventilates the ocean and provides and pulls the CO2 out of the atmosphere. I mean, in equilibrium, the ocean would really control atmospheric concentration, because there's way more carbon in the ocean. This ocean has about the same amount of carbon as the atmosphere, but the deep ocean has, 40 times as much carbon. And you could think of it that the ocean would control it on long enough time scales. But we're in disequilibrium, and the ocean takes 600 years to equilibrate. So the trying to get the CO2, this extra CO2 into the ocean, it really only occurs in these high latitude cold spots. Or you can have some, the other way it occurs is that at the surface of the ocean, you can have marine biota bloom, and then the carbon fall as organic carbon, is marine snow, they call it, and it can fall down. And then that way you can get also the carbon down to the deep part of the ocean. All right. So there's a lot of fluxes of carbon going on. And we're lucky that about the land and the ocean take up on kind of short time scales about half of the emitted anthropogenic CO2. They pull it in. And that means that our warming is half as much as it would have been if this feedback wasn't going on. But will this continue in the future? Especially if you deforest, can't happen on land, and the ocean is heated from above, and so it has this really slow turnover time. But also you heat it more because the accumulation of the CO2, then we might well shut down that ventilation. That's what people think is happening. And so then this marine biota actually becomes more important. Also, that we want to keep the marine biota blooming, and then with that organic carbon that's basically the biota falling to the bottom of the ocean, that allows some of the carbon to get down. So aerosol deposition can impact the oceans in a couple of ways. The main way that we think is the most important is through iron. So iron is an important micronutrient. So you don't need too much of it, right? And we don't need too much iron, but we need some iron, right? It's in our US RDA. You guys in Europe, you also have a recommended daily allowance as well. The iron is an important micronutrient, and some regions of the ocean are what's called high nutrient, low chlorophyll, HNLC regions. And that's here, what we're seeing here is the amount of nitrates here. This is the nitrate concentrations in the ocean, estimated from observations and intelligently extrapolated here. And you can see that there's extra nitrate here, there's extra nitrate here, and extra nitrate here. And it turns out there's low chlorophyll, which I'm not showing you here. And chlorophyll, we can see from space, and it's the greenness, basically. And it tells you if there's a bloom there, if there's a phytoplankton bloom or not. And so it was a big, when I first came to graduate school, this was a big debate, is why are there HNLC regions? And John Martin made the argument it's because they're missing iron. And so you notice that none of the HNLC regions are anywhere close to the big dust sources. So here, there's some in the Southern Ocean, but you're still pretty far from South America. And then, of course, the Asian dust plumes aren't as big as the African ones. And this North Pacific HNLC region is actually seasonal. It's not always there. So he speculated that actually it's due to iron limitation, and some of the other arguments were grazing and all sorts of other things. But people went out and fertilized in the ocean and showed that actually in these regions, there was iron limitation. And if you throw iron in, you get a bloom. And so that's where these red experiments show where there was observed iron limitation, where if you throw iron in, you will actually get a bloom. And so you can see that in the end, John Martin was correct about what was driving the HNLC regions. And so what that means is that the iron in the dust actually gets into the ocean and relieves that iron limitation. Some of this occurs on longer time scales. For example, you won't, for a lot of phytoplankton, the small phytoplankton, they won't be iron limited, even in some of the some of these regions. they'll be more nitrogen limited or phosphorus limited, because the iron, it kind of sticks around. There's like, they have colloids and other ways to keep the iron in the solution. But on a 50-year time scale, we showed in a 2018 paper, actually a lot of the ocean gets iron limited if you don't have any dust deposition. So the dust deposition really matters for maintaining the upper ocean iron amounts. In addition, nitrogen fixtures in the ocean actually have higher iron requirements. And a lot of the ocean is nitrogen limited, not iron limited, right? The rest of the ocean. And so that's very powerful. And it's kind of like a catalytic reaction. You add a little bit of iron, you get a whole bunch of nitrogen potentially. And so that's a way to link the nitrogen and the iron cycles. This has been seen, this is in a recent paper that showed that there is an ocean response to strong dust events. So you remember the dust is about 3.5% iron, or, it has hematite as well as a bunch of other more bioavailable minerals. And then the chlorophyll is what you see from space, and you see the greenness of the phytoplankton. And so here's the percent change in chlorophyll a few days after a large event. And you can see in many regions, you get a statistically significant result. So the ocean is more productive after a dust event. You can also see the changes in the ocean phytoplankton ecosystems as well in studies and other studies. So here again, we're talking about, not all dust is equal, and the iron in the dust is really important. So for the EMIT project, we had to kind of choose one reason to think about what the importance of EMIT was. You can see that there's all sorts of things we could have chosen, but what we, because we could have gone for the ocean biogeochemistry or whatever, but we ended up choosing the solar shortwave. And for NASA missions, you got to be pretty narrow and make sure you can meet your requirements. So for the EMIT mission, we chose to look at the shortwave impact, and our goal was to reduce the uncertainty in the shortwave impact of dust. So what we did then, and how I got involved, was my graduate student in 2015 published a paper where she built a model speciating the dust in a model. And then we showed that it was important, basically, but that we didn't have very good data sets. So I'm going to talk to you a little bit about the infrastructure here. So, so this is a pre-EMIT estimation of what the global distribution of hematite was. And we stick that into our model, and we have, the spatial distribution. And then we emit dust. And then we, have properties of the dust. We have different compositions, different sizes. So instead of having one dust, we have 8 types of dust. And then in this particular model, we have 3 different sizes of aerosols as well. We get the radiative properties, and then we can, get the 3-dimensional distribution and get the scattering and absorption inside the Earth system model. So we use the FAO data sets, Food and Agriculture Organization, soil data sets, and the average minerals in each soil type. Okay. So we take the global distribution of hematite, we multiply by the dust emissions, and then we can get the spatial distribution of each mineral, illite, kaolinite, morlite, hematite, right? And so we get those in the model. We have the 3-dimensional distributions, and then we can calculate our radiative effects. So how pre-EMIT, how did we get our distribution of minerals? Well, this is we didn't have that much data. We basically had 80 soil samples from FAO sites. And if you look, of course, FAO is Food and Agriculture Organization. Of course, most of the soil samples are not in desert regions, because why would the Food and Agriculture Organization go to desert regions, right? So most of the samples aren't really what we want. And then we kind of use the averages of these and we extrapolate to the world. So we're extrapolating very few soil samples to the world in this approach. There's kind of 2 different ways to do it. There's the Clark-Henn et al. Approach in 1999, or the Journet et al. Approach. And they get really different values of iron oxides. And so and iron oxides really matter for their radiative properties, as we'll talk about. So this isn't the best approach. It's wildly extrapolating. So Longley Lee wrote this paper just varying every different parameter that you could vary to see what are the key uncertainties to the radiative effects from dust, and the iron oxides dominate it. So here's our dust DRE, direct radiative effect in the short wave in watts per meter squared. And you can see it in this model is about minus 0.18 for most cases, but if you increase the iron oxides in the clay fraction or the silt fraction, you get more warming, less cooling. Or if you play with a complex reflective index, which is basically the same as changing the iron oxides, that also matters. And then it depends if you use the Journet et al. Or the Clark-Kent. You get really different warmings from this. So the most important part of our uncertainty turns out to be the amount of iron oxides in our data sets pre-EMIT really made this very, very different from that estimate. So we had a lot of uncertainty just because we don't know. No one goes out and makes soil samples in the middle of the deserts. And what EMIT does is it takes advantage of the fact that minerals have very distinct spectral signatures. And so, for example, this kaolinite has this absorption band right here. This is the reflectance. So if you're looking at the ground and the incoming solar radiation is reflecting and you're standing here with an instrument measuring that, this is how much is reflected. 1 would be 100% reflected. 0 means absorbed. And then we can see this across different wavelengths. And of course, the visible extends, like this is the visible range, and then here in the near infrared here. And you can see that there are some very strong absorption bands here for kaolinite. So if you have this kind of spectral resolution, you can tell you got kaolinite because it's going to have an absorption band there. Or down here with goethite and hematite, these are the iron oxides, you get absorption bands here. So you can use that. Now you can't use like the mean reflectance because it could be wet or it could be some other impact. You have to use the difference across the spectrum, basically the solar spectrum. And but you can see here, these are not wetland samples, but the iron oxides have much less reflectivity than a lot of the other minerals. So that's you can tell it's darker also here in the visible range. So it turns out at the same time that we were showing that the composition matters, for many years, they've been flying what's called an imaging spectrometer on a airplane called Avris and making maps of the mineralogy in different regions. And so this is what the JPL folks have been doing and really perfecting these imaging spectrometers. And so you can see, the composition retrieved from the Avris flights over, this is the Salton Sea. So the idea was then to take, this instrument and instead of putting it on an airplane, put it on the space station and then use that to try to detect what the composition is. Let's see. So, and then you can also go out in the field. This is one of our collaborators out in the field. He's doing the control right here, but then go straight down and take a look at what is going on. So here they're doing the spectroscopy at the Salton Sea, so they can check that this image is correct and that the retrieval is actually working well. And so in the EMIT project, we combined those two, right? The need to have the composition at the surface in order to get the radiative forcing, which is why I became the deputy PI, because my student had built that infrastructure for that. And then the JPL part was build the instrument, put it on this, put it on a rocket, take it up to the space station, and deploy it. And so we were focused. The prime mission was focused on these desert regions that have the desert dust. So the EMIT instrument draws from a long history of imaging spectrometry. It didn't come out of anywhere. They've been doing this since the 80s. And, Rob Green has really been one of the leaders in this. And so it's amazing what you can do with these imaging spectrometers, as we'll talk about. So all this great stuff happened. So what is the result then? Like I said, that paper just came out yesterday, so I'm going to show you some of the images from that. What we did was we took the, instead of the pre-EMIT 80 soil samples, I think, I can't even remember, 40 billion, 40 trillion samples of what's going on at the surface. The mapping occurred at 60-meter resolution of all the desert areas over, for the prime mission, it was just 1 year. So we took that composition, then we stick it in, and we get the surface composition. Then in the model, we use that information then to change what the sources were. So instead of the pre-EMIT data sets on the soils, we actually have EMIT data sets then that are actually observed instead of extrapolated. And we put that into our models, and we get the dust aerosol mineralogy, and we can do the with the radiative properties, we can show then what the impact was. So our goal of EMIT was to reduce the uncertainty in the dust radiative effects from mineral composition. And the first thing is we reduced the uncertainty in our airborne iron oxide fraction by, 60–80% here, because before we had the pre-EMIT, we had either the Cloquin or Journet approach. And now we've actually, to extrapolate the limited data, and now we have actual measurements. And all these studies are done using multiple models, because one model might have bias. We have 4 different models included. We can improve our estimates of the direct radiative effect efficiency. So the radiative effect is really kind of difficult to get observations, because what it really is what is the top of the energy balance with dust minus without dust. And models are good at that, but that's really hard to observe. But there are some observations of that where you have a dust event, you can look at the radiative balance, and without a dust event. And so we use these then to try to understand the direct radiative effect. And so we have these observations, which are in the gray here that we're trying to match. So this is over land, and then there's several different observations over ocean. And you can see, there's different models here. The red is with EMIT, and the blue is the pre-EMIT. And you can see for all the models, it improves what's going on over land. And in general, there's one, too high here. You can just see that the red ones are always closer to the observations. But maybe not in this case, but in general, the red ones are much closer to the observations. So it improves our estimates of the direct radiative efficiency from all the different models. We get a new estimate of the direct radiative effect here. You can see here, this is our dust shortwave direct effect. And, most of the dust comes off of North Africa. You see the Middle East, you see Asia a little bit. And so you get, almost no effect over the North Africa, right? And that's consistent with the observations here. It's close to 0. And I mean, basically, whether the dust is in the atmosphere or on the ground, it has the same scattering effect. And so that's what you're seeing here. You don't see the impact of the dust over the desert regions. You see it over the dark surfaces close by. So here we have the forests right below, or over the ocean. That's where you see the cooling. So those are really dark surfaces, and the dust reflects more than those. If we went over ice, the dust would have caused warming instead, because it changes the sign there. So we have a huge decrease in the regional uncertainties. And you can see this spatially, and you can see here. So, our goal was reduce the uncertainties, and making direct measurements reduce the uncertainties. It's really true. You can see this also in this plot, which is the Dust shortwave plot. We can talk about the uncertainty and the uncertainty pre-emit from the iron oxide amount, basically, or a composition amount, was this amount, and it goes down to here. There's definitely uncertainty across different models. And then we can also look in the future. There's uncertainty also. We don't know what's going to happen in the future. So we ran a bunch of future scenarios. And you can see that the composition pre-emit was one of the largest uncertainties. And we basically bring the uncertainties down with emit. So success, that's what we were meant to do. And it just means, making observations instead of extrapolating wildly gives you a better estimate. So there's other things that you can use the emit, the amazing emit instrument for. So actually, I think the prime mission ended in 2022, I think. But emit has a little bit more. You can see that they made it, the instrument, they built it under COVID. Here, when it blasted off going up to the space station, we had a little party. And here's some more images and NASA has the best images. But there's other things you can get with this imaging spectrometer. For example, you can get at 60-meter resolution the ecosystem diversity and the leaf mass and other things, because again, there's a spectral signature of these. You can get snow grain information. Lots of different examples. I want to talk a little bit about the remote measurement of methane and CO2. These show up in the near IR, and which is measured by emit, and you can see the plumes really easily from the imaging. And so you can see methane coming out of a landfill, coming out of, or CO2 coming out of power plants. And this is super powerful. 60-meter resolution. You think you have a leak in your pipeline, but you don't know where, right? Well, this instrument can tell you where it is down to 60-meter resolution. I mean, it can really help people figure out with the fugitive emissions of methane, especially. And so it was a really big success. So the EMIT instrument is still on the space station because of these other applications that it's good for. So that's all I wanted to talk to you about. I hope I convinced you that dust aerosols are important. You guys are dust people, so you believe this. And EMIT provides amazing data to help us understand the composition of the dust. And EMIT has a whole lot of other applications. So thank you very much. I'm happy to answer some questions here.
Thank you very much. I think we have a few questions here.
Oh, Franco.
Thank you very much, Natalie. This was very, very interesting and fascinating talk. Welcome also to the DustDN network. I have several questions, so I will ask one, and then I'll see if anyone has more questions. Otherwise, I'll come with more. But I'll start with this one. Is EMIT a one-off mission on the space station, or is there any plan to let's say continue the experiment after the EMIT mission?
Well, originally we were supposed to only go up for a year, and there was somebody scheduled after us, but it was so successful and they're so excited about the data, we're still up there. Rumor has it we'll stay up until the space station dies or the instrument dies. Okay, so there's the data. I see Diana, hello. The data is all freely available. So there's, the spectral data is all up there, but the composition data is also up on the web. The model output, all the stuff I showed is available on the web. And I think the NASA interface is actually excellent. So please go and get it, and you can get it for specific events, or you can get kind of climatologies also.
Thanks. I'll shut up for a while, and if nobody asks more questions, I'll ask more.
Let's see. Oh, Claire. Yeah. Hello. Glad to answer any questions.
Hello. Thanks for a fantastic talk. I think the answer to this question is probably no, but is EMIT able to tell us anything about the composition of dust in the atmosphere?
So, yeah, right. That's the big question. People are looking at it. So I mean, the first round, we were trying to get the composition. And of course, it's so much easier when it's sitting on the ground. Okay. But the idea is to go to look again at repeat events and see if we can see any composition in the atmosphere. Right. So people are working on it. At this point, I do not know of an event where people got a really clear signal.
Mm-hmm. Okay. Thank you.
I see Helen had a question about why you don't see the radiative effects from emissions over the deserts, but over the surrounding dark regions. And that's because you know, if you're in a desert region, you've got a pretty bright surface and the dust is the same color. Like you can just think the dust is the same color on the surface of the earth or in the atmosphere. And so it just doesn't change the albedo that much, you can think. Okay, so then you won't see it in the direct radiative effects. All right, sorry, I interrupted someone else's question.
No, I was just saying that there are more questions in the chat.
Okay, let's see. And then Evelyn asked about the mass fraction. Let's see. Yes, so the EMIT gives you information about, you know, what the dominant mineral is, but also the composition at the surface of the earth and the percents for different types. You know, here I just emphasize the iron oxides because they matter the most for two problems, but it's there for all 8 of the EMIT minerals. It's all available. Let's see, someone else. Wait. Oh yeah, please.
Hi, Dr. Mahowald. Thanks, a very great talk. So I'm Jiang Yu. I'm from NASA Goddard. So I just have a question about. So it's a great work of constraining the shortwave DRE using the EMIT, but I know that the EMIT right now, because it's covering shortwave to near infrared, right? So the sensitivity for feldspars and quartz, they're not very sensitive. So there's no retrieval or no estimation for quartz and feldspar, right? But there
Yeah,
are
that's
so many
absolutely true. I
important-
didn't say that. Yeah, we cannot
It's
get
fine.
any information about quartz or feldspar. We had to use other data sets to get those. Yes, it's a good point.
Yeah. So I wonder, like, if we want to, you know, using some more infrared hyperspectral data to further estimate those fractions, do you think that's kind of like a good directions to go to, like estimating also the fractions of quartz and feldspars in the soil?
Yeah, so yes, someone else has to do it because EMIT can't do it. Now, there was a paper by someone who is associated with a group whose name I've totally ditched on right now, but she had figured out a way from other instruments, or maybe a little bit of the longer wavelengths, getting the quartz fractions.
Right.
But yeah, that wasn't the intent of the EMIT mission, and we didn't do a good job with it. And it's still a super important question. And it, you know, and it changes the answer even for the EMIT part of it, because you know, the quartz tends to be bigger, and it kind of changes also your retrievals, what
Yes.
fraction the main bulk of the mass is. It changes the
Right.
retrievals. So yeah.
Great. Thank you.
Thank you. Yeah. Hopefully newer versions will include better estimates of the quartz from remote sensing and will improve all the parts of it. You know, I didn't mention it, but calcium, we have a separate paper that was just published that I led, that looked at the you know, the calcium, aluminum, iron, silica, and titanium, and coming out from EMIT, and compared it to data. And we knew that we had a problem with some of the calcite because it's not seen very well. And indeed, the calcium was low in the observations we show in that paper. So we do a pretty good job with iron oxides, but there's still issues. And we hope in the future we can refine those.
Anyone? Okay, Franco has more questions.
Happy
And
to
only
answer
if
your
no one else
questions,
has,
Franco.
only if there's no one in queue, no one is queuing. Yes, so something I've always wondered, and is, EMIT will give information on the composition of the soil in the source regions, in the desert regions, but this soil will be made of different types. I mean, there will be heavy old rocks that have been there for hundreds of years. There will be dust, very fine particles, even though they're deposited on the soil. They might not even be local. They might have been transported there from a nearby place. So how does it disentangle the picture? Because the big rock that's been there for hundreds of years and will stay there for another hundreds of years, probably not very relevant for the atmospheric science like the other ones.
Yeah, so we removed the consolidated, we had a GUM mask. What does that mean? The global unconsolidated mask. So we were only looking at the regions. We masked out the regions where there's a big rock or the whole thing is bedrock. Okay, so we're only looking at the regions where there's sediment around that could be entrained. And then we use information about the size of it, and in the retrieval is part of it. It actually changes the retrieval what the size of the soils are. Some of that
But
information.
the size you have from a different source than from the.
Yeah,
EMIT.
I'm trying to remember because we did it like 5 different ways, and they're trying to do the size from the EMIT and from the remote sensing. But I think that we were unable to get that to be robust for this first version. But we're hoping in follow-up versions that we would be able to retrieve that kind of separately and use that information, from the same pixel to get information about that's self-consistent there. But that's a really tough problem. We'll see if that works. I see Helen asked about volcanic ash emissions. Of course, we can't see it in the atmosphere. We're not really trying to at this stage. Maybe if we accidentally went over a volcano with and without a volcano, we might be able to do something. But in Iceland, it's the volcanic material that actually gets entrained. However, Iceland is too far north. The space station doesn't go that far north. So I'm not sure we can help with volcanic ash at this stage.
That's why a little bit why I was asking if there is going to be any other mission that's going to continue the work of EMIT, maybe on a polar orbiter or.
Oh yeah. So I mean, EMIT continues, but and now I'm going to forget the name. There's EcoStress that's going to go up. That's going to have an imaging spectrometer. I'm not an imaging spectrometer person, but I was surrounded by them for this experiment, and they were so excited about this. They think it's the future of everything, and every mission will have imaging spectrometers. So they would say, yes, this is only the starting point. Okay, so there'll be more missions. Okay. Let's see, we got another question, Ahmad.
Yes, thank you. I have one question about your last slide, I think. I want to know, could you please give us some information about how did you retrieve all CO2 concentration or methane concentration from the spectrometer? Is it something like dose measurement, or which techniques did you use?
Yeah, so I didn't have anything to do with it, but I think it's so cool, so that's why I present it. So on the slide here, they're using the fingerprints. It looks like the methane they're using an absorption between 2,000 and 2,400. And then for the CO2 fingerprint, they're using an absorption band at about 2,000. So, I mean, they're looking specifically at different bands, seeing the depth of it to figure out how much is there.
True. Okay. Okay. So
Okay.
maybe you find one very clear absorption line and focus on that and detect that one. Yeah. Thank you.
Right, and then use that depth. So that's Andrew Thorpe led that, and he's got a couple really nice papers describing how to do it. So check it out. Yeah.
Yeah, for sure. Thank you.
Let's see the data access link. Let's see, you should be able to. Oh boy, I never I never do that. I get somebody else to do that. So it's called the NASA DAC Land DAC. Let me see if I Google it, if I come up with the right thing. Here's the link. It's called the DAC. There, and just Google for emit data, and then all the different levels will be available. So like the model output is like level 4, okay? But before that, I think you might want level 3 will be the mineral compositions, but some of the like the global distribution of the mineral compositions normalized and everything that we used as the input to our model is actually in the level 4. So you want to go to the level 4 for that, okay? If you're looking at much higher resolution, you want to look at the level 3. And if you want the reflectances, then do level 2 probably. Any other questions? Franco probably has more, but.
General question. Yeah, we don't many things we don't know about dust. We cannot easily get from remote sensing. We don't know the size of the particles. We don't know the shape. And well, now thanks to EMIT, we know a little bit about the composition. Which one do you feel? Probably doesn't have an answer, but which one of these do you feel is let's say the most important one, or the most one that affects most the climate, or yeah, which
Yeah,
one
so
should we address?
we have papers about this, so I can actually answer. So I mean, we showed that the composition was the most important uncertainty to begin with. Now that we have this, then we think it's the size, and so that's in a GRL paper that should come out soon, hopefully.
Okay, thanks. That's great that you have a clear answer to this question, which I thought was going to be
Well,
like an open question. That kind of
oh
worries.
no, well, from the beginning, I mean, we started this in 2018. Everybody's like, well, don't we need to know the size? And don't we need to know the shape? So anyway, like people have been asking us. So then we're like, good question. And so we went and we looked at it. And, you know, it's model output and everything, but that's what we think the most important are. And, you know, other people may disagree, and I hope so. And, you know, go and take a look at it, and then let's see what we can constrain.
If anyone else has any questions, if not, if they come up with questions at a later time, they can always contact you through via your email, I guess.
Absolutely. So happy to talk to dust people. So wonderful.
So thank you very much for joining us today. I would also like to briefly share this, that we have a page. If is my screen visible?
No?
No. Now? Yes. So
Yep.
we have this small Friends of Dust DN thing where people who are interested in our network and are happy to join with the community can just look it up, and we'll be happy to have you as a friend of the Dust DN. And we have summer schools and conferences also once in a year, and it was very nice having you here, and thank you very much.
Timothy, maybe you can remind how many webinars every how many months we think to have a webinar?
We try to have at least once a month, but it sometimes becomes once in 2 months, and this is the third one. We are all students. We are organizing and hosting these webinars, and thank you.
Yeah, so I would like to highlight this, that all the webinars been organized by our students, and they have, like we can see that they organizing this very, very well. They selecting the speakers also very well. So this is great, and this is one of the important things in our network that the students are very active as well as let's say the old ones.
I think we can close